Okay, today we're going to do section 6.4, which is on the Dirac delta function. And the first thing I have to do is fix this. The Dirac delta function isn't really a function, it's a distribution. But we're going to treat it like a function, and we're going to derive it from a function, so that kind of counts, all right? Okay, to derive the Dirac delta function, let's first look at what we want it to do. So this will be f and t. And here's what we want the Dirac delta function to do. It's supposed to model what are called impulses. And impulses occur in physics all the time. In mechanics, impulses occur in collisions, and they occur when we want to drive any sort of a harmonic system. It basically means we're going to hit it really hard. You can also think of an electronic impulse as when a capacitor discharges. So what happens is this function is zero everywhere except at one point, and at one point it becomes massively large. We're going to actually say it has infinite magnitude right there at point C. And that's of course what makes this a non-function. We're going to write down the symbolic notation of it. The Dirac delta function uses the Greek letter delta, and it kind of looks like the letter 8, except you don't quite finish it. And it's t minus c. So this would be the Dirac delta at point C, which means it's infinite right here and it's zero everywhere else. So that's its definition, is that it has a magnitude of infinity as long as t is equal to c, and it's got a magnitude of zero everywhere else, so otherwise. Now, of course, this guy isn't a real function. It's not a real function because it has an infinite value. It's not a real function because we can't integrate it. We can't integrate it because it doesn't have any width, so I couldn't plug in upper and lower bounds. So it's got all kinds of issues with it, all right? So what we want to do instead is model it with another function. I'm going to call this f of epsilon. And f of epsilon is also going to be t minus c. And in order to build f epsilon, it's also going to be piecewise defined, and I'll show you what it's going to be. We're going to widen this thing out and give it a definite height, okay? We're going to call the lower limit right here c minus epsilon. And the upper limit right here is going to be c plus epsilon. That means the width of this is 2 epsilon, and that's what we're going to call the height. The height of this guy is 1 over 2 epsilon. And we make those choices for good reasons. If this has a width of 2 epsilon and a height of 1 over 2 epsilon, it's got an area of 1. And that's what I want the area of the Dirac delta to be. I want it not just to be an impulse, but I want it to be a unit impulse. And sometimes the Dirac delta function is also called the unit impulse. Well, let's look at what that does to this f epsilon, okay? So it's going to, again, f epsilon t minus c, it'll also be piecewise defined. And what it basically means is anytime I'm in between these ranges, it'll be 1 over 2 epsilon, as long as c minus epsilon is less than or equal to t is less than or equal to c plus epsilon. And again, it's 0 everywhere else, so otherwise. Well, the good news is this guy is actually a function. It's a function because it has a height, it has width, I can actually integrate it, but this isn't actually the Dirac delta function. It's really close, but you'll notice this guy doesn't have infinite height, this guy's got an actual width, and neither of those are properties of the Dirac delta, all right? Again, to prove that this guy has a magnitude of 1, well, we can see it just by the area, but I can also take the integral of this from 0 to infinity, so let's do that. So if I do the integral from 0 to infinity, just to show that this f epsilon is matching what I wanted, it'll be of f epsilon dt. Now, of course, from 0 to infinity, f epsilon dt mostly has a 0 value. It only actually has a value from c minus epsilon to c plus epsilon. So let's go ahead and change the limits from c minus epsilon to c plus epsilon, because everywhere else the function's 0. We don't need to integrate from 0 to infinity, we just need to integrate between these bounds. And between those bounds, f epsilon has a magnitude of 1 over 2 epsilon dt. Okay, so that's going to be t over 2 epsilon between the limits of c minus epsilon and c plus epsilon. and I think everybody can see what's going to happen here. This guy's going to be c plus epsilon in the numerator minus c minus epsilon. So it's going to produce 2 epsilon over 2 epsilon. The c's will cancel, and that's equal to 1. So I know that the area under this is 1. And now here's what we'll do. This is like the coup de grace, right? I'm going to take the limit as epsilon goes to 0 of f epsilon. And what is that going to do? Well, it's going to squeeze this guy together because epsilon gets smaller and smaller and smaller. And at the same time, it gets taller and taller and taller. And what's the limit as this guy goes to 0? Well, the limit of this little box here, it's going to keep its area of 1, but of course it's going to turn into the Dirac delta function of t minus c. So this is the real definition of the Dirac delta function. That's why it's not really a function, it's a distribution, because the function itself is the limit of another function. And the limit of a function tends to be a number, not a function. And that's why this guy doesn't really quite qualify as a function. But it now does mean that we can integrate it. Because we could integrate this, and we showed that this is equal to this limit, notice how the limit doesn't influence the value of this integral. This integral is the same no matter what epsilon is. So as epsilon goes to 0, this still retains its value of 1. So now I can say that the integral from 0 to infinity of the Dirac delta function, t minus c, is actually equal to 1. And that's good news because, boy, we could never have integrated this before because this has a magnitude of infinity at c and 0 everywhere else. Yeah, good luck taking the integral from c to c of infinity dt. Like, that is not going to give you 1, right? But we proved it with the function that models it. Therefore, we proved it for the Dirac delta, all right? So that's the Dirac delta function. Let's take a look at how we can go about using it then, now that we've done some of these properties of it, okay? So let's go back up here to the top. The first thing we want to do is look at what happens, just like with the Heaviside function, when we multiply this by another function. So if I were to take g of t, just any general function of t, and multiply it by the Dirac delta of t minus c, what impact would this have on this function? Well, to see that, let's go ahead and integrate it from 0 to infinity, gt of the Dirac delta at c, dt. Well, you can see this is really interesting. Because the Dirac delta function returns 0 everywhere except at c, this will be 0. The whole integrand will be 0 everywhere except at one value, c. And of course, g at c is no longer integratable. It's not even a function of t. It's just the value of g at t. So I can pull it outside the integral and say this is g at c times the integral from 0 to infinity of the Dirac delta function, t minus c dt. And we just proved that this was 1. So if I multiply a function by the Dirac delta and integrate, it simply returns the function value at wherever the Dirac delta activates, okay? That's important because the very next thing we want to do is this. Remember, keep in mind the whole purpose for the Dirac delta function, the reason why we introduced it now, is we want to use it on the R function in non-homogeneous differential equations. And we're going to use it because that R function, remember, is the input for the diffie-q. And if it contains a Dirac delta, it means it's an impulsive function. It's one that takes on a large magnitude at one point, but it's 0 everywhere else. Well, if this guy is going to be on the right-hand side of a differential equation, and I want to use the Laplace method for it, one of the first things I've got to do is be able to take the Laplace transform of the Dirac delta. Okay. So what is this going to look like? Well, once again, it's the integral from 0 to infinity of e to the negative st times the Dirac delta, t minus c, dt. Well, we just saw what this does. It's why we introduced this guy right here. This is called the sifting formula, by the way. It sifts the function down and just returns the one value where the Dirac delta activates. It's going to do the same thing right here. So this is the definition of the Laplace transform, and when it's Dirac delta, it's simply going to kick out the e to the minus sc as being the only point worth integrating. And then the remainder, when this is inside, is just 1. So that's it. This is the Laplace transform of the Dirac delta. It's e to the minus sc. And you'll find that on your table of Laplace transforms. All right? That's pretty much it. The only other thing I wanted to show you was just as a tie-in to our Heaviside function from yesterday, when we had that f epsilon t minus c, and we were using it as a model of the piecewise defined function 1 over 2 epsilon whenever we're at c minus epsilon less than or equal to t less than or equal to c plus epsilon and 0 otherwise. Remember, the Heaviside function is really good at turning piecewise defined functions into pseudo-continuous functions which are defined everywhere. So let's do that with this guy, right? If it has a value of 1 over 2 epsilon, then we can write, hey, this is equal to 1 over 2 epsilon. And then I can use the Heaviside function to turn this condition on and off. This is a step function, which means it steps up to have a certain value for a while, and then it steps back down again. But I can use a difference between Heaviside functions to do that. So this will be the Heaviside function at c minus epsilon, because it's 0 all the way up to that point, so it'll be 0 otherwise until we reach this condition, and then this guy guarantees that it turns on and starts producing this, and then I'll subtract the Heaviside function at c plus epsilon. Remember what this guy is. This guy's 0 everywhere until we reach c plus epsilon, and then it turns on and becomes 1. Well, this one was already 1 because this condition is met before this one. So all the while we're in the middle of the range, this guy will produce 1, and when we reach the end of the range, this will go back to producing 0. So there it is. This is a continuous function, fe. So this guy, again, if we take the limit as epsilon approaches 0, then this is also another representation of the Dirac delta function. So you might see interactions between the Heaviside function and the Dirac delta because they are closely related. All right? Okay, in the next video, I'll show you an example of how we're going to apply this to solve second order ODEs.